went over a little bit, but then the student had a question. It started to be about research paper, and it got off into space travel, and it just kept growing. I thought, where is this going? When will it ever end? But let's get started from the current slide. I'll even turn on the projector and go over the announcements just briefly. I don't think this will apply to anyone in this class, but if you know of someone it might apply to, please sure to let them know. Tomorrow is a date they list as the 60% completion date for full-term courses in fall term, okay, for Title IV funds. I think that's just about any federal financial assistance. And what I think the bottom line of all this is, why they keep up with it and track it and stuff, is because if a student is on federal financial aid and withdraws from a course before the 60% date, then the student is liable to pay the money back. The school definitely has to pay the money back to the federal government, and the student is liable to pay it back to the school. So the point of that is, I think, to discourage students from withdrawing too early. After tomorrow, I think it's safe. Now that's for full-term courses. Second mini-term course, that's a while yet into the term. Okay. I think that's it for the administrative calendar. Our volleyball team will be hosting Bevel State Community College over on the Birmingham West Campus, Arthur Shores Fine Arts Building, which is also our gymnasium. And that match is at 6 o'clock this evening. And it's a really, really good team. So our volleyball team is. So it's well worth effort to try to go by and see them. I'll be here until after 6, so I probably won't be able to get there. Okay. Any questions on anything we've done so far? Oh, there is something. I finally finished grading the test that had been turned in. Now, my work study student has managed to do all sorts of weird things with the filing. But here is your test 1. Oops. You've got 2 parts of your test 1. Okay. 1 test listed as test 1, test 2. What's that? Oh, no, not from this one. Good score. In fact, I think it was the top score, but. Yep, it was. Okay. So, no questions. We left off in Chapter 13, Functions of Several Variables, 13.5, the chain rule for functions of several variables. Top of page 912 in this section, and we had just on the previous page 911 had talked about theorem 13.6, the chain rule for one independent variable. We had that, and this is what it says about that. The chain rule in theorem 13.6 can provide alternative techniques for solving many problems in single variable calculus. For example, in example 1, you could have used the single variable technique to find the w dt by first writing w as a function of t. That problem we did last time, I don't have it listed here. W is equal to x squared y minus y squared, where x was sine t and y was e to the t. And the way we did it was the dw dt was do partial w with respect to x times the x dt, and plus the partial w with respect to y dy dt. Worked it out. We got this. Well, if you had plugged in what those were to begin with, and then this would have been e t sine squared t minus e 2t, and then differentiated, then this would have been a product rule here and a power rule there. And this has a power rule in it, and chain rule in it, and all sorts of stuff. You'd have gotten the same answer we did before. I think the technique we used before was probably easier, shorter, less work than this one is. But either one of them works. So whichever one of them is easier, that's the one to go for. And here's Josh. And for your present for coming in today, here's your first test. And it's a gift. No, I'm just kidding. You did well. All right. So we just have finished going over this first slide. Oh, I'm sorry. This may have been... No, this is the bottom of page 911. The chain rule presents, this is at the bottom of that page. We came up with the same answer. We did this last time, I think. Okay. So this is where we should be, right here. Okay. Sorry. The chain rule for theorem 30, see, the wording was the same. I thought that's what we were. The chain rule in theorem 13.6 can be extended to any number of variables. But the 13.6, remember, you only have one independent variable. In this case, it was t, okay? But you can have any number of intermediate variables, okay? So that's what we're talking about, extended to any number of variables. For example, if each of x of I here is a differentiable function of that single independent variable t, then if w is equal to some function of all those functions, intermediate functions, then dw dt. All right, here's Corey. Perfect attendance today. Good deal. Okay, and there's your gift for coming in. Here is your first test. Good deal. Well, all right. And if you have any questions about those, anytime, good to ask. Okay. Right now, any other time, once you've looked it over, if you don't see why you missed something, I'll be glad to try to work it out. I may have made a mistake grading it, so please let me know. So, if you have this function w of all these intermediate functions, x of 1 through x of n, but each one of these is a function of the variable, single independent variable t, then your dw dt, since there's only one independent variable, dw dt would be the partial of w or f, you can call it either one you want to, with respect to x of 1 times dx1 dt, because these are all functions of that single variable, plus the partial of w or f with respect to x2 times dx2 dt, plus ... all the way down to the partial of w with respect to that last one, x of n, times the dw dx of n dt. Okay? Just extending that one theorem 13.6, which was just for two intermediate variables now, or functions, to n intermediate variable or functions. All right, I've got to sneeze, I'm sorry. Wow. Caught me. Okay. Now, they're skipping examples 2 and 3, so let's back up and do example 2 here. And by the way, I don't know if you count this lucky or not, but my first class this morning, Cal 2 class, the PowerPoint slide was corrupted. And I taught from it last summer, and it was all perfectly fine. Same everything, so something had happened. And so I couldn't write on the screen, so I had to do, it would project on the screen, but I couldn't write. And so everything was done in red marker, so that if you see a pinkish tint here, that's why, because we had to do all that. So people who weren't here, there's only one person who wasn't, will have to sort of follow along. So here's example 2. Two objects are traveling in an elliptical paths given by the following parametric equations. The first path, x of 1, is 4 cosine t, and y sub 1 is equal to 2 sine t. Okay? X sub 2, this is the second path, second object, is 2 sine 2t, and the y value for the second object is 3 cosine 2t. Okay. First object, second object. The question, at what rate is the distance between the objects changing when t is equal to 5? So, at what rate is the distance between the two objects changing when t is equal to 5? And I'm going to try to come up with a, let me use the same thing. Okay, they use S. I was going to use D, but they're using S. So what we're looking for is ds dt. When it says rate, that's almost always with respect to t. Okay? Doesn't have to be. Well, they tell you here when t is equal to pi. What we're looking for ds dt when t is equal to pi. That's what we're looking for. Okay? Now, we have it. What S is the distance between the two objects. Okay? So, they jump right into the formula, which I guess is okay. I would have been tempted to write it first as a R1 of t, R2 of t, and then the distance between them was I'm sorry, the square root of R1 minus R2, okay, square, yeah, and do it that way. They're just jumping directly into the distance formula, and they're just doing x1 minus x2 squared plus y1 minus y2 squared, or they're doing x2 minus x1. It really doesn't matter because you're squaring. So what the S is here then, using theirs, so I won't have to try to be reconciling the two different approaches, be the square root of the change of x's, x2 minus x1 squared plus, yeah, y2 minus y1 squared, okay, which is just a difference in their coordinates, you know, which is basically what we would have been doing had we written it as a vector. But that's your distance formula. I don't want to use that as my derivative, to take a derivative of. I would write this as x2 minus x1 squared plus y2 minus y1 squared to the 1/2 power. Okay, well, don't need a parentheses and a bracket. Let's just use the bracket. Okay. That's how I would write it to take my derivative. Okay? Now, again, just like they were telling you on the last slide, you could put these values in here and get it all as functions of t's, and then do your squaring and all like that, and then do your derivative directly from s to t. I think that would get pretty nasty, okay? There'd be so many variables to keep up with. So I think it's easier just to do your partial of this with respect to x2, and then do the ds2, dx2, dt, and do that for all 4 variables here. So, which way would you like to do it? Plug in the x's for functions of t in here and do the square root that way, or would you rather use the chain rule and keep the intermediate variables or functions here?
Why can't you do the derivative of the last equation and substitute after you?
Yeah, I think that's the way to go. All right, so ds dt is partial of s with respect to, you tell me how to go. X sub 1 dx sub 1 dt plus partial of s with respect to y sub 1 dy sub 1 dt plus the partial of s with respect to y sub 2 times dy sub 2 dt. There it is. So, the only sort of difficult part here is taking these partials with respect to the various variables here. So let's start with this first one. What's the partial of s with respect to x1? Start with the outermost function. That would be the 1/2 times this whole thing inside the parentheses. x2 minus x1 squared plus y2 minus y1 squared to the minus 1/2. Is this really the easy way to do this? Yep, that's what they're doing. That's the first step. What's the next step? You're doing a chain rule here before you even get to the next variable. What would be the next part of this? Okay, we're doing the ds, here is your s here. the ds, well, I like this form better. The ds with respect to x sub 1, this one right here. Well, s is this function here, so you do 1/2 of this thing to the minus 1/2. That's what we got written here. Then the chain rule says, then take the derivative of the inside with respect to s1, x1. This part doesn't have any x1, so that part's going to be 0. So what's the derivative of s with respect to x1 here? Two times this thing to the first power, right? Then you have a minus, because the derivative of x1 here would be a minus 1, x1, and then ultimately we'll do the dx1 dt, which we'll do from here. Okay? So there's lots of pieces here. Don't lose any of the pieces or the puzzle won't go together well, okay? So the next part here is 2 times x2 minus x1, bless you, to the first power times a minus 1. So I'm just going to put the minus in front of the 2 there. Okay. Now, I need a lot more space than what I've got. So I'm going to take this up here. First thing I'll do is, here's a 1/2 here, here's a 2 there. We can wipe those out. Okay, for this partial with respect to x1, okay, here's what we've got. A minus x2 minus x1 over that square root. And I don't know if I want to write it as a square root or a... Yep, they do. So let's do it. The square root of x2 minus x1 squared plus y2 minus y1 squared. All right. So that takes care of this one. Then we got a dx1 dt. That's pretty easy. dx1 dt is what? Minus 4 sine t. Okay, so that minus and this minus will go out, and we have a 4 sine t. Already, hopefully you'll see there's some problems here. You got t's, you got x's, you got all sorts of things, so we're going to have to come back and reconcile those. But that's what that one is. So we've got this term done. Okay, your partial of s with respect, with respect to x2 is going to be just like this, okay? So I'm going to cheat a little bit and put a 2 here, and that would be the first part is just the same. The second part, though, is you don't have the minus sign. You have 2 times that, and then derivative of x2 is 1. So that will then be plus x2 minus x1 over that same square root. Everything's identical in that square root because that was the same thing we did before. Then you got the dx2 dt. Yuck. Okay. And what would that be? derivative of x2 dt. Anybody? 2 cosine t. So up here, whereas there you had a 4 sine t, this is a 2 cosine t. All right. Now let's move to the ds dy1. Well, that's just going to be just like the first part of this is exactly the same. The only difference there is it's going to be a 2y2 minus y1. If I can find my work here. Yeah. But there's going to be that minus in there, so that's going to be a minus. Again, the 2's are going to go out just like they did before. Minus x2 minus x1. No, I'm sorry, these are y's this time. Okay, to the first power, and your denominator is going to be the same. So this is going to be that same square root, so I'm going to write that again. And then you have dy1 dt. What is dy1 dt? A little louder. 2 cosine t. Okay? So we don't lose the minus sign here. So you have that denominator, and you have a 2 cosine t. Whereas before. Oh, but look. Oh, no. Not quite. I thought we could eliminate those two, but we can't because of the x squared minus y. x2 minus x1 minus x is the first one, and y2 minus y1 is the second one. So we can't do that. We can factor it out later, but let's get back to this. And then finally, your partial of s with respect to y2 is going to be a plus. And that's going to be your y2 minus y1. That's going to be still there if my 1 will ever print. Okay. Over that same denominator. That hasn't changed. That part's the same. And then you have your derivative of y2 with respect to t, and that would be what? Minus 6 sine of 2t. So this has a minus. So let's change that plus to a minus. Okay. And this will just be a 6. Just had it written down somewhere. There it is. Sine 2t. Okay. Whew, boy. Now, when t is equal to pi, and that was what the question was, yeah, there it is. When t is equal to pi, what is this derivative, ds dt, the rate of change of that with respect to time when t is equal to pi? What's that?
Minus 4 times 0.
Okay. right up here, yeah, this one will be a 0. Okay? This one will be a cos. Is what? The second one there. I thought you started with this one right here, 4 sine t, which is going to be part of that, and that was 0. The next one was a 2 cosine t. What's the cosine of pi? -1. So that's going to change that back to a minus, and that will leave us a -2 times this thing. Well, I ought to write it in. x2 minus x1 over that square root. All right. Minus, and cosine again is going to be a -1, so that's going to be a +2 times y2 minus y1 over that square root. And then the last one is going to be a 0 again. Okay. So we're down to 2 terms now. And they have a lot in common. And what we probably ought to do is go on and evaluate what these functions are. We've been dealing with the derivatives, which we did there. Let's also evaluate the function at, so x1 at pi is going to be -4. y1 at pi is going to be 0. x2 at pi is what?
0.
Yeah. And y2 at pi is going to be, okay, wait a minute though. When t is equal to pi, 2t is 2 pi. Cosine of 2 pi is, yeah, did you say 3? Okay, I thought you said -3, sorry. Okay, it just dawned on me you did say it correctly. Okay. So let's see what we've got here. Let's just calculate your s here, because that's what shows up in your denominator everywhere. So this would be the square root of x2 minus x1, 0 minus a -4 is 4, plus y2, which is 3, minus 0. Okay, this is root 7, I think. And that's exactly what your denominator is here, is the square root of 7. Every one of them. Okay? So this is square root of 7 down here. I think, what's that? Oh yeah, okay, yeah, you do. Sorry about that. I've got to find where I just did that. x2 minus x1 boy, I've got myself. Okay, here we go. x2 at pi is 0. x1 is so that is 16. You're right. This is a 16 here, and this is a 9 there. And what's the square root? What's 16 plus 9? And square root of that is 5. So this is 5. So So that's your denominator everywhere, is 5. Goodness, this is all over the page here. That's why they took an entire page plus to work it out. I don't have that luxury here. So let's see what we've got. The x2 minus x1 was a plus 4, if I'm not mistaken. But we had a minus 2 in front of it, didn't we? Yeah, well, the minus 2 was from our dx dt, I believe. So these are 5s in the denominator. Let's see what our So it looks like to me, if I'm not done something stupid here, this would be a minus 8 over 5 would be this one, minus 2 times a 4 plus 3 minus 0, 6 over 5. So this would be a minus 2/5. Now I probably, no, 22/5. Yuck. We got the 5 right. We got that part right. Without having a lot more room to work on it, I can't follow my own writing here, so sorry about that. If you use the book, it pretty much pairs it up pretty well for you. The ds dx1 is minus 4/5, and I've already, but we don't really need that because that's multiplied by dx1. So all we need is the ds2, and we got a plus 6/5, which is what we got, and the second part there was a plus, there's where it was, 16/5. I had written down 8/5. It's 4 by 4, not 2 by 4. So I think I got these two crossed up. So this, I think, was supposed to be plus 4. So that gives us plus 16. And yeah, plus 16 plus 6 is 22/5. Man, what a miserable set of circumstances there. Now, if we had had more room and spread it out, I think we would have kept track of it a little bit better. And I think I was a little late plugging in my t is equal to pi. I think you could have done it a little sooner than I did and probably would have straightened things up. But we had all the numbers in place, so I just got them crossed up there. But you came out 22/5. That is a sort of a bear of a problem, okay? Distance formulas usually are, okay? Because you have squares, roots of things squared, added, you know, and stuff like this. There's so many pieces in them. That's what it got. And honestly, I don't know what is the easiest way to do this problem. There's no easy way, but you just have to keep up with your variables a little bit better, or the values better than what I did. But I can see where they came up with the 22/5. So. All right. Now, they also skipped example 3. So let's do that one. Hopefully it'll work out a little bit better. In example 2, note that S is a function of 4 intermediate values, variables, x1, y1, x2, y2, each of which is a function of the single variable t. Another type of composite function is one in which the intermediate variables are themselves functions of more than one variable. And that's what we're going to do next, and they do it with very little PowerPoint support here. They just jump into example 3. So let's clear what we have here and do example 3. Hopefully it won't be quite as messy as that last one, because the last one just had way too much for me to write on one slide, and I couldn't think of a way to erase enough of it without erasing something I needed. So here we're finding a partial derivatives by substitution. What we're looking for is partial of W with respect to S and partial of W with respect to T for W is equal to 2xy, where x is equal to s squared plus t squared, and y is equal to s over t. And let me go on and write this as s times t to the minus 1. Okay? I think that's going to be easier to work with later. Okay. Okay. We want to know what the partial of W is with respect to S, which is your one of your two. Okay. Here's the situation. W is the single output variable. Okay. Two intermediate variables, x and y, where x is dependent both on S and T, and y is dependent both on S and T. So you don't have a derivative of W with respect to S because there's two independent variables, so even this has to be a partial derivative, even though there's only one output variable. Okay? So we need to write down what these various things are. So let's do it. Let's start with partial of W with respect to S. Tell me what theoretically that will be. Start with this part. We're not going to plug in yet, but just tell me, what would that be? Partial of W with respect to X times partial of X with respect to S. Right? You see it? Okay. What would be the next one? Okay. Y times partial of Y with respect to T. No, S. See, we're not doing the T's yet. Okay? Say again? Oh, I erased the S, a T, and put a T back in there. Okay, sorry about that. Is that what you were saying?
Oh, that's a question. Put it up on the what you're saying.
I was saying, like, I was saying, because you had said you're not doing T yet. I was like, T has its own section, like, you have to do,
Everything's with respect to S to begin with.
right now.
X, Y, both with S. Now the second part is what? It's T, and that would be would be again with respect to x, but this time the x, a partial of x with respect to t, t, plus partial of w with respect to y times y with respect to t. That's it. Okay. So we've got a couple of things to do first. First, we need to figure out what the partial of w with respect to x is. What would that be? 2y. Okay. We also need to know the partial of w with respect to y. And that will be 2x. We also need to know the partial of x with respect to s. 2s. This is getting dull, isn't it? And we need to know the partial of x with respect to t. 2t. Now here is where things get a little weirder. Partial of y with respect to s is 1 over t, or t to the minus 1. Right? Got it? And the partial of y with respect to t. This is the part I don't like. It's not bad. Minus s over t squared. Or st to the minus 2. Okay. Now, once you get those done, it's just plug them in the right places. Okay? And the partial, well, that's the first part of the next step. Yeah. So this will be 2y times 2s, right? Here's your 2y, there's your 2s, okay? Plus 2x times 2, where is that? dy dt. That's an ugly t here. There it is. Minus, no, it's s. Yeah. 1 over t. I'll write it that way. Okay? Now, in a sense, that's your answer, but it's not really. Okay? Let's go ahead and plug in these. dw ds, we already had that before, is 2y times dx dt is 2t plus, and curly d, I keep saying it wrong, partial of w with respect to y is 2x, and partial of y with respect to t is negative s over t squared. Okay? But we've still got to go back to our, see, we want this with respect to s, this with respect to t, so we want s and t to be our independent variables, not x's and y's. So we need to plug in what y is. So this will be 2 times s over t, that's your y, right? Okay, times 2s plus 2, and your x is s squared plus t squared over t. Okay? Same thing down here. 2y, that would be 2s over t times 2t. Ha! That's nice. Plus and your x is 2 times s squared plus t squared okay over over t squared, but also times a minus s. This is a little awkward, but I think doable. Okay. So what do we have here? Your curly dw to curly ds would be 4s squared over t plus 2s squared plus 2t squared all over t. So this would be 6s squared plus 2t squared over t. I think. Okay. All right. 6s squared plus 2t squared over t. Yes. All right. Let's do sort of the same thing down here for this one. And I think you get a 4s to lead off with here. And then you're going to have a minus (2s cubed) minus 2t squared, st squared, yeah, okay, over t squared. All right. Now, it seems a little bizarre, but if you multiply this by t squared and divide by t squared, then you have 4t squared minus 2t squared is 2st. Oops! I can't read my writing. That is a squared. Okay. I thought that was a cubed at first, but I just multiplied it, so it was a square. Minus 2s cubed over t squared. I hope that's the answer. 2s squared, 2st squared minus 2s cubed over t squared. Yeah. All right. So so a lot of it is bookkeeping. Yeah. Getting all your stuff, making sure you've done the partials correctly, and then make sure you line them up and put them with what you need to, and make sure they work. My bookkeeping on the previous one was really sloppy. So, but you just need a lot of room to do it. This was a much simpler problem. You only had 2 independent, 2 intermediate, 1 other. The last one we had, what was it? 1 independent, 4 intermediate, and 1 output, final result. But it was just a lot more to keep up with. And you had the square roots and the squares and the pluses and the minuses. Yeah, it was real easy to get lost in. This is pretty simple here. Just a product there, a sum of squares there, and a quotient there. So made for a little bit easier tracking, I'll put it that way. So theorem 13.7 gives an alternative method for finding partial derivatives in example 3 without explicitly writing w as a function of s and t. Now we didn't. We did we did the alternative method, okay, which I think worked out pretty well. Otherwise, well, I think it's about 6 of one, half dozen of the other, okay. I wasn't paying attention to what the book did. I just looked at their answers, and we got the same answers, but they plugged in what X and Y were, which functions of S, X and Y were as functions of S and T, and then took a derivative that way. So here is your theorem 13.7. Let's see if we can get that to come up. Okay. Chain rule for two independent variables. This is actually what we did. Let W be a function of X and Y. We had that. For F is a differential function of X and Y. Okay. And X is a function of G of S and T. G of S and T. Y is H of S and T. Such that the first partial is partial of X with respect to S, partial of X with respect to T, partial of Y with respect to S, partial of Y with respect to T, all exist. Then the partial of W with respect to S and partial of W with respect to T, partial of W with respect to X is partial of W with respect to X, partial of X with respect to S. That's hard to distinguish what I'm saying. Plus partial of W with respect to Y, partial of Y with respect to S. Kind of this tree diagram down here. And the partial of W with respect to T is partial of W with respect to X, the intermediate variable. First time, the partial of X with respect to T, plus the partial of W with respect to Y, you have the partial of Y with respect to T. Okay, and this is how they do this. Since you have two intermediate variables and to each independent variables, all of these are partial set. When you had only one independent here, they come back together, but not here. So this is your partial W with respect to X, that with respect to Y. This then is your partial of X with respect to T. Why don't they have the S's and T reversed? I don't know. Partial of X with respect to S. And so the partial of W with respect to T would then be the partial this, that. Partial of W with respect to S would be this one, that one. Partial of W with respect to Y would be this one, that. W with respect to T, this one, that one, and partial of W with respect to S, this one, that one. Which is exactly what we wrote down here. I don't know if you find the trees helpful. They're pretty, but you may not find them all that helpful. Okay. There is an example 4 here, and this one you can see at larsonCalculus.com for an interactive version of this type of example. Now this looks like what we just did, isn't it? Isn't that exactly the problem we just did? Yeah, and we've already done it. So the first time they changed the X, okay. Example 3, which probably I've erased now. Yeah, I've already erased it, sorry. They first changed everything to S and T. The W, they put in what X was and they put in what T was. In this one, they're doing what we did, which is using theorem. I wondered why they had us do it and then gave you the theorem afterwards. Well, I thought, well, fine, maybe they wanted us to work it out ourselves. But you can hold T constant, differentiate with respect to S, which is exactly what we did. Okay? And later and that's 2y, 2s. Look familiar? Exactly what we did. we actually wrote out what the partials were up there rather than just doing them in our heads down here. I think that may be a little better, especially when you're first getting started at it. Maybe after a while you can do it without that. Okay?
Just to keep everything nice and neat.
What's that?
Just to keep everything neat. Where
Yeah.
You don't mess up.
I think it helps. Okay? And hopefully that looks pretty familiar. Okay. We've done the second part here. And you see, we did before it coming out exactly the same. 4s was this is 6s squared plus 2t squared over t. Now, in my mind, I would have written this as this one, and this one is plus 2t. And go on and divide out the t. But I noticed the book didn't, so I didn't either. But that to me is a little simpler to write. But then that was our second one. And we had already figured out what partial w with respect to s, x with respect to t, w with respect to y, and y with respect to t. Just plug them in, which we did. And that comes up with a this was our y. So this gave us something over t. But then the 2t here, I cancel out, so we got 4s just like we got. This gave us minus 2s squared over t squared minus 2st squared. I'm sorry, this is s cubed. This is st squared over t squared. And this was just a 4s, not over anything. So if you put it 4s squared over t squared, then that combines with this one minus 2s squared. So that, see how they do it. They just magically write it down. No, they do. They do fine. This is 4s over that, just like we said. Just like we did. And then made that 4st squared over t squared. And you subtract the 2st squared from 4st squared. You get 2st squared minus 2s cubed over t squared. Let's see, I would have wanted to take this one more step and said 2s minus 2s cubed over t squared. They don't do that. It's fine. This, I guess, is easier for typesetters. Not simpler to write, but easier for typesetters. Okay. Bottom part of page 914. Don't let me run over. Okay. The chain rule with two independent variables under that problem that we just did. Chain rule in 13.7. Bottom third of the page of part 1. There in 13.7 can be extended to any number of variables. Now, what are they talking about here? Any number of intermediate variables and any number of independent variables. Still only have one dependent variable, okay? Completely dependent variable. So if that's the case, where you have n intermediate variables and m independent variables, okay, then what your w is when it's a function of x1, x2, up to x of n, you obtain the partial w with respect to this first independent variable. That's the dependent with respect to the first independent. Partial w with respect to x1, partial of x1 with respect to t1, plus partial of w with respect to x2 times x2 with respect to t1. You have all t1s down here. Okay, and you keep going this way till you finally get partial of w with respect to x of n, partial of x of n with respect to t1, and then you do it for t2 all the way through, then t3, all the way up to partial of w with respect to t sub m, partial of x1 with respect to w with respect to x1, then partial of x1 with respect to x sub t, x of m. Goodness gracious, t sub m. Okay. Can't talk. Partial of w with respect to x2, that was a partial of x2 with respect to tm. Keeps going all the way till you finally get partial of w with respect to xn, partial of xn with respect to tm. Please don't have too many of these out there. If you can imagine that each one of these you're having to do a partial of your w with respect to each one of these, and a partial of each one of these with each one of those. I mean, the numbers multiply exponentially, because especially when you get the partial of each of these with respect to each of those, because you got m with that one, m with that one, m with this one, m with every one of these. So m by n, you got that many, and then you have the partial of w with respect to this, so another n of those. So it's m plus 1 times n. And if those are very big at all, even 3 by 2, that could be lots of calculations to do, and then getting them together in the right combinations. Can be harrowing. Okay. They skip example 5, which I bet you is going to involve these. So let's back up and see if we can get example 5 done in here. Find partial of w with respect to s and partial of w with respect to t when what? S is equal to, okay. Can it be this simple? I'm going right up here. S is equal to 1 and t is equal to 2 pi for, this is your function, w is equal to xy plus yz plus xz. Okay? Where x is equal to s cosine t, y is equal to s sine t. That's tough to write. That's ugly writing. Let me see if I can make it a little bit better. That's not Scott, scotched or something like this. S times the sine of t. And z is equal to t. Do we have enough here? Okay. It's funny, this is what threw me. They gave the values to do it at in the middle of the problem before they gave you all the problems. I was going, whoa, okay. So, I don't know. In my mind, not a bad idea to go on and do all the partials somewhere. And then it's going to be, I think, a little easier to put them in. So they say. So what's the partial of w with respect to what you want to do first? X, what would that be?
0.
Second?
It's just S cosine t.
Okay, wait.
Oh, I'm doing it right there, my bad.
Yeah.
Y.
Y, a little more.
Oh, plus Z.
Y plus Z. Okay? Partial of W with respect to Y, X plus Z, and partial of W with respect to Z.
I would go ahead and do 2X plus Y.
No, that's a Z.
Oh, no, just X plus Y.
X plus Y. Got
I was
it.
thinking the first one was X, Z.
Right. Okay. It's really ugly writing here, and it's up here in the red, so it's a little hard to see. That's X plus Z. It's getting worse every time I mess with it. Let's also do our partials with respect to S and T. Partial of X with respect to S.
Negative S.
Second?
Partial of X with respect to S.
Partial of X with respect to S.
So negative S. Sine.
Okay, wait, okay. For X and S and T, there is no S dependence in the trig function there. It's only the S is out front. That would simply be cosine T. That's the constant. The partial of this thing with respect to S. This is a constant, like 7S. The derivative, the partial of that would be 7. Because S is in the first column there. That's the variable there, S. That's just cosine T. You see that? Okay. Now what you want to do next? Partial of Y with respect to S. What would that be? Sine T, okay. And the partial of Z with respect to S. Nope. T is a constant. If you're taking the partial with respect to S. 0. Okay. Now let's do the Y's, and we still got to do the Z's. Okay. I think I said that wrong. No, we did it right. Okay. Partial of X with respect to T. That's the one you were trying to do before. What's that?
S for negative S. Sine T.
Sine, is that what you said?
Yes.
Sine T. You're right. I don't hear well, so partial of Y with respect to T.
S cosine.
S cosine T. And the partial of Z with respect to T, 1. Got it. Okay. Now if I can find where I've written all that, I think I've got it all written down. 3 partials with respect to each of your dependent variable with respect to each of your intermediate variables, and 3 partials, the 3 partials with respect to intermediate variables of the first independent variable, and then the partial of the 3 intermediate variables with respect to the second independent variable. I think we got it covered. Excuse me. So first, theoretically, tell me what partial W with respect to S is.
Which one, I'm sorry?
Partial W with respect to S.
Okay, so we got that curly dw EX.
X times
Curly EX.
partial of X with respect to S plus
Partial W.
with respect to
Partial
Y times
Y.
S plus Got it. Okay. Now, do you want to work those out and then later do partial of W with respect to T, or write down what?
Well, let's go ahead and do that.
Which one? Continue here?
Yeah.
Okay. W with respect to X. That one's up here. Now, it's Y plus Z. So you want to go and write down what Y plus Z is in terms of S and T? Or not? You want to? Is that okay? Is that skipping too many steps?
Well, I think it makes it easier if we just go ahead.
Second?
I think it makes it easier if we go ahead and plug it in and just write whatever the...
Okay. Plug in just what we have here. Is that what you're saying? Or plug in. Okay, right, plug in. Okay. Okay, Y plus Z. This is going to be Y plus Z, but Y is S sine T. S sine T plus T. Is this what you mean?
I was talking about plugging in S and Z also. I guess just everything all at once.
Say again now.
I was talking about plugging in everything all at once. Like,
Okay, well that's what I'm doing at once, but, or did you want it 2 steps? Text is 2-step or 1-step?
I was going to do one.
Okay, well that's what we've just done. Here's Y plus Z here, and here's Y plus Z here. Right? Okay. Times ds partial of X with respect to S, that's from up here, that's cosine T, right? Okay. Plus partial W with respect to Y is X plus Z, so that's S cosine T plus T times partial of Y with respect to S, and that's sine T. Agreed or not? Okay. Plus partial W with respect to Z is X plus Y, and that will be S, I'll write it out, cosine T plus S sine T times dz ds, which is 0. Okay, sorry, could have saved ourselves a little effort there, because dz ds is 0. So we didn't need that term. All right, so let's, can't believe we don't have any minuses in that, but have I left them out somewhere? Oh, there it is. There's a minus. Knew we had one somewhere. Yeah, okay. All right, so this gives us S sine T cosine T plus T cosine T. Is that right? Plus S cosine T sine T plus T. Huh?
we can go ahead and make that one 0 too, right?
Maybe, but let's not write yet. Okay. Plus T sine T. These, the reason that went to 0 is this one right here. We don't have that down here yet. Maybe when we plug in, it's going to be okay. It will be. Because, yeah, but let's hang on for a moment here. Okay. So I think we've got it all in S's and T. Now we can plug them in. Well, sine of 2 pi is 0. So this is going to be 2 pi, and cosine of 2 pi is 1, right? Okay, so that's just 2 pi. Sine of 2 pi is 0, and sine of 2 pi is 0. So yeah, all those go, our answer there is 2 pi. All that to get 2 pi. It just doesn't seem fair, does it? Okay? Now, partial of W with respect to T. What would that be? Start with the chain rule. Partial of W with respect to what? X times X with respect to T plus partial of W with respect to Y times partial of Y with respect to T plus partial of W with respect to Z times T. Alright, let's go back and plug in. Partial of W with respect to X was our Y plus Z, which is S sine T plus T. Now, I can almost hear Josh saying, can't we go on and set that equal to, at least the first part equal to 0? And we can. That's going to be 0. Okay? Times ds dt, the x dt, which I have down here, is minus s times sine t. That's going to be 0. Okay? We're done with that. Both of those are 0. Am I right there? Yeah, because that was times. I put a plus, but that's supposed to be a times, isn't it?
Yes, sir.
Okay. Yeah. Plus partial of W with respect to Y. Well, that's our X plus Z, and the X is S cosine T plus T. Yeah, because it's Z. Okay? That times, and frankly, looking back at it, as soon as we got these written out, we could go on and write down what their values are, rather than hauling them around this long. I just haven't, but I should have. As soon as we wrote them down, we should have plugged in these values. And then we wouldn't have to be keeping up with them like this. Partial of Y with respect to Z, T, is S cosine T, and that's S cosine T. We'll write that one down for now. Plus partial of W with respect to Z, X plus Y, and that would be the S cosine T plus S sine T, which we know that's going to be 0, times the partial of Z with respect to S, no, Z with respect to T. I know I've got it here somewhere. There it is 1. Okay, so it's just 1. So, plugging in, this first one completely went to 0. This is going to be 1 times 1 is 1 plus 2 pi times 1, right? Okay, plus 1 plus 0. So it looks like we got a 2 pi again, doesn't it? Or 1 plus 2 pi. Plus 1. So it's 2 plus 2 pi? Yeah, 2 plus 2 pi. All right, because this is the 1 plus 2 pi times 1 plus 2 pi. This is just a 1, so it's 1 plus 2 pi plus 1. I started to put a plus 0 there, but I didn't. I'll do that just so it won't be confusing. Okay. And it's 2 plus 2 pi. Actually, I guess since we already knew those were going to be our values, as soon as we had written these out, we should have put those in. And as soon as we had written those out, we could have put them in. And those out, we could have put them in. So then we would have just had numbers to work with. But you have to keep up with them too, which is standing for what. All right. We've got a few minutes. Let's see if we can at least get started. Anyone need this up a little longer? Okay. That was example 5. That was the stuff at the bottom of page 914. Now, implicit partial differentiation. Ugh. This section concludes with an application of the chain rule to determine the derivative of a function defined implicitly. In other words, you can't write y is equal to f of x or something like that. So let x and y be related by the equation f of xy is equal to 0. Okay? That's what we've got. Some combination of things there. Where y is equal to f of x is a differentiable function of x, to find dy dx, you could use the techniques discussed in section 2.5, whoa, way back, okay, Cal 1. You will see, however, that the chain rule provides a convenient alternative to doing that. Consider the function w is equal to f of xy, which is then also capital F of x, comma, little f of x. Okay. You can apply theorem 13.6, which is this derivative of w with respect to x. And now both of those x's are independent. You know, that's the independent variable. You don't have a y in there. That's the partial of f with respect to x at xy times dx dx, which we know what that is, 1, plus the partial of f with respect to y at xy times dy dx. And if this is what we're looking for, then what we do is subtract first this from both sides, and that would be derivative of, see, is that what we're looking for? Yeah. Derivative of w with respect to x minus the partial of x at xy, and that's just 1, and divide that by partial of f with respect to y at xy. Now, that's verbiage. Let's actually see it written, okay? Because w is equal to f of xy equals 0, for all x's in the domain of f, little f, not big F, know that the dw dx is also 0, okay? Because w is 0 and dw dx, okay? That's the key here. So then your function is f of x dx dx, which is 1, plus f of y at xy dy dx equals 0. Solving this for this, subtract this from both sides, and then divide by that. Now, if the partial of f with respect to y is not equal to 0, you can do this, okay? As long as this thing is not equal to 0. That's it. Now, this looks a little bizarre, at least it feels like it to me. The partials don't seem bad, because dy dx, okay, this is partial with respect to x over partial with respect to y of the same things. And since this is with respect to x with respect to y, you can kind of think of those as being inverted and multiply, giving you partial with respect to reality. That part seems okay. What seems a little strange is the minus sign, okay? But it is correct because you subtracted that from both sides. Similar procedure can be used to find the partial derivatives of functions of several variables that are defined implicitly, okay? and they don't really say how, but it can be done, okay? So here's the theorem. .8, which is the top of page 916. We're rapidly running out of time here. Implicit differentiation. If the equation f of xy is equal to 0 defines y implicitly as a differentiable function of x. Okay? Defines y implicitly as a differentiable function of x. Then the dy dx, that's the slope of the y with respect to x, is minus partial of f with respect to x over partial of y with respect to f, as long as that partial of y with respect to x is not 0. If the equation f of x, oh, they are going to show for 3. xyz is equal to 0, defines z implicitly as a differentiable function of x and y. That's the part that I wondered how they were doing this. X is a function of, but it's z with respect to then the partial of z, because now you have two independent variables, x and y, okay? Partial of z with respect to x would be minus the partial of f, which is this function here, with respect to x at those three values, the minus of that over partial of z. So you see in every case, your subscripts reverse the order. This one goes here, this one goes there, minus signs there. But then you also have a partial of z with respect to y, and of course the partials go in the opposite place. You always have a minus. In both cases here, the partial of z cannot be 0. If it is, you don't have to define other partials, or derivative in that case. So, do we have time to work an example? What do you reckon? Say again? 4 minutes. Well, there's actually 2 examples here. Let's see if we can get the first one done. Here it is. Second?
It seems easy.
I can't hear.
It seems easy.
Yeah, I think so. So, dy dx, and this, by the way, is your capital F of xy. Okay? That's what that is, because it's set equal to 0. If that was equal to minus 4, you move the 4 over here to make it equal to 0. Okay? And what does the theorem tell us it was? Minus remember?
F sub x.
Okay. Minus f sub x at x and y over f sub y at x and y. Okay? They don't give us any value for x and y, so we're going to have to just leave it as that. So this is, you first need to figure out then what f sub x is. And what would that be? Second?
1x, so it's negative 2x.
Negative 2x. Perfect. And f sub y is?
3y plus 2y.
3y squared.
Yeah, plus 2y.
2y.
Minus 5.
Okay. Now, the only little problem here is this thing here that f sub y cannot equal to 0. Okay? And we can look at that in a moment. So this would be minus a minus will be 2x over 3y squared plus 2y minus 5. Okay? As long as 3y squared minus or plus 2y minus 5 is not equal to 0. Let's see if it could be. What value would that be if it were? Can that be factored as a 3y and a y? And this will be plus 5 and minus 1. Does that work? What you think?
It's the same term.
Is that correct?
The same term.
I'm sorry.
I said, look at the same term. Is that 2y up there?
Yeah.
Well, how you gonna get that out of M plus N dollar minus 7?
That is.
Yeah, this is a plus 5y and that's a minus 3y.
Okay.
Okay. And I think it works, doesn't it? So this is as long as y is not equal to minus 5/3 or 1. Okay. As long as it doesn't, there's your derivative. Okay. And they don't call those into play at all.
Even though that's pretty important, right?
What's that?
That's pretty important though, right?
I would think so.
Unless they're counting the 4 as, that will never happen.
What's that again?
Never mind.
Yeah. So as long as those two values aren't met, I don't know why they left them off here. They say you can go back and look at example 2 in section 2.5. I'm sure y'all want to do that. But we're out of time, aren't we? So we're going to have to pick up next time with example 7. We almost finished this, folks. Just missed about that much. Y'all don't remember Maxwell Smart, do you? Okay.
No idea who that is.
Okay. It was a dumb show, Get Smart.
I've heard of that.
Yeah, it's back, well, they had a movie a few years ago that they redid that. Homework exercises here in section 13.5. Either 3 or 5, they're both at Calc Chat, 3's at Calc View. Any of the odds 7 through 11, they're all at Calc Chat, 9's at Calc View. 13's at Calc Chat. 15 or 17 are at Calc Chat, 15's at Calc View. 19 or 21 are at Calc Chat, 19's at Calc View. 23 or 25 are at Calc Chat, 23's at Calc View. 27 through 33 are at Calc Chat, 31's at Calc View. Let's stop there and you can we'll pick up the rest of those next time. Okay. All right, good deal. In fact, that last group, 27 to 33, you can hold off those because that's 3 variables. We didn't get to do 1 with 3, so we'll do that next time. Stop at 25. All right. Any questions? All right. You need the book at home soon?
Yeah, I got work.
Okay. Do you want to get started right away, or do you need a little time? I'm sorry?
I probably do about 2:15.
I can't hear, sorry.
Class too long. I really don't want to be in class too long.
Right.
So,
Okay. But you want to go and get started? I got to go and swap books, but then...
you don't have to be at risk. That's how I probably get my test.
I'm sorry?
I said 9 times out of 10, I probably just get my test.
Okay. So you want me to go get the test? Is that what you said? I can't hear.
Yeah, I said 9 times out of 10, I probably got to just get my test and I'll just go. Yeah.
Okay.
I said, you don't have to be in a rush to,
I don't have the test with me. I've got to get it on my office. Okay.
Yes, sir.
Okay. So are you going to stay any, or are you just going to get your test and go? Huh?
I can stay for high C.
How much?
I can stay for a high C. I can stay for a high C.
For, I still can't hear. For what?
I can stay for me.
Okay. All right. Let me go swap out then. So y'all take advantage. Well, I've got to shut this down.